I'm Conrad, one of the co-chairs for the PyData Global 2021 conference. We're super excited today to have Ian Ozsvald talking to us about the state of higher performance Python. Thanks, Ian. Please take it away. Oh, and quick note, the format is a quick presentation with discussions afterwards, so please stay on mute until the discussion time. Thanks.
Thank you very much, Conrad. Hello, everyone. So my name is Ian Ozsvald, and as Conrad says, I'll be giving a brief update on the state of higher performance Python. If I pause or take big breaths, forgive me. I'm 2 weeks into a cold because my son has started at nursery and we are doing the journey of priming a young immune system. And unfortunately, Dad finally got nobbled by one of those colds as well. But I'm pretty clear, I think, so we should be good. So today's goal in 10-15 minutes is to talk a bit about where we are in the world of Python, thinking about data scientists and quants, so people doing numeric calculations, particularly looking at tools available for profiling, compiling to go faster, where Pandas is at now and some of the new things in Pandas, and scaling to larger data sets, and also reflecting on a journey that many data scientists don't take, which I teach in one of my courses, on finding bottlenecks, so figuring out what's slow so that you can go faster. Because performance isn't just about finding the right tool, the fastest tool out there, it's about the whole development process. And this bottleneck discovery is a critical part of that process, which is often overlooked. So I'll talk a little bit about that. And then we're going to end with some Q&A. We can talk for as long as we want during the course of the hour around topics that are bothering you. So I'm super keen to hear where you are in your journey, which things bother you, block you, what you can't solve, or you've solved but inefficiently, and maybe there are some better ideas. Maybe you found a good solution that you want to share. I'm super keen to hear any of those ideas later on. So who am I? I'm a chief data scientist. I've been in the field of Python and C++, high performance computing and data science analysis for 20 or so years. I often work with teams now at a strategic level, helping teams make sure they deliver things of value. I used to go and write the code to solve data science problems. So I've done lots of machine learning, I've done lots of data manipulation and preparation, lots of dirty data handling. And now I try to help teams take an efficient path through all of that. I also really care about high performance computing. So there's a picture there on the right of my book. This is the second edition. The first edition was a bit thin, but the second edition was a nice meaty book. Super proud of that. Published that with Misha Gorolik a couple of years ago. Here we're going to touch on some of the tools that are mentioned in the book, but also a couple more that have appeared in the meantime. I'm sharing from topics from my high performance Python class that I run. That's a public and a private class. I've also got a cheat sheet which comes out of that class, which I'll share and put into the chat at the end of this talk, which might give you some new tools to go and investigate with. I'm also one of the co-founders of PyData London, a huge community in London, part of the 180 PyData meetups around the world. So I'm really passionately involved in this community and have been for 8 or so years. So where are we at? If you're a data scientist, then of course you'll be using Pandas. It's the default tool. It actually forms a bedrock tool now, which other tools are growing on top of. So it's kind of becoming a platform. It's an interesting tool. It's been developed in a kind of an ad hoc fashion over the years. It doesn't have a unified, clean underlying design. That's kind of being added as it matures. And so we have little oddities, like you can easily use 5x the memory that you would expect to be using, which can get, of course, pretty painful. So might there be ways of understanding that? And yes, of course there are. Profiling is ignored by a lot of people to their misfortune. I teach that in my class. I talk about it in many of my public talks. There's a whole bunch of chapters on it in the book, and I'll give you a couple of slides to guide you there now. And then there are misapprehensions out there. So, hey, Python's interpreted, it's single core, it's got the global interpreter lock, which is awful. We don't know why it's awful, it's just awful. It can't scale to larger data sets, so we should just give up on it and go to another language. Some of you may have seen in the TOB language index that Python recently jumped from number 3 most popular language on the planet to the number 1 most popular language on the planet, and there's a reason for that. And sure, there are all these cases that do cause us problems. It's not the perfect language for all use cases, but it's a pretty good language for so many use cases that it's risen to be one of the most popular on the planet. So what kind of tools help us solve our problems? So One thing that a lot of data scientists don't do is analyze their code at all. And there's 3 different profiling tools that I'm going to mention here. One is Line Profiler. This is an oldie, but a very goodie. So this has been around for over 10 years, downloaded millions of times every year by users, but it's still relatively unknown. So I like to highlight it. It's one of my go-to tools, one of the first tools that I go to. It's a deterministic line-by-line profiler. You can use it in the Jupyter Notebook. You can use it at the command line with your modules of code. And it's brilliant if you've got numerical code like NumPy or Pandas that you want to analyze, particularly single-threaded, single-process numeric code that's got some tight loops. So you want to look at a couple of functions, understand why they're slow. This will tell you, you can see in the screenshot at the bottom, there's 3 lines that have been profiled. 2 of them taking 25% of the time each, 1 of them taking 50%, the one taking 50% does a bunch of math operations. That kind of makes sense. But why do the other 2 lines, which just do some dereferencing, take so much time? It's because of the overhead of Python being a dynamic language. And hey, maybe that makes you think, well, maybe I need to go past the dynamic nature of the language. Maybe I could compile this in some way or specialize that code. So I found Line Profiler really helps me spot what's slow, so I'm not focusing on the wrong problem. And then it gets me thinking about how I might go and solve it with other tools. VizTracer is a relatively new tool, it's certainly new for me. It does the same kind of job as Line Profiler, but it breaks out graphically in the web browser this call stack, this flame chart, showing all the calls that go on behind a public call. So right at the top is my function doing something. That calls into a bit of pandas with the mean function, and that calls a whole bunch of pandas cascading down with functions calling functions, and then time is represented by the width of those lines. It works in the notebook, it works at the command line, and it's great for drilling into complex code. For me, it's opening up pandas rather than digging through the source code and trying to understand what's in there. Instead, I run this on my pandas code, and all of a sudden I see a million functions being called, and it lets me get creative. I can see one way of doing a group by or a query, and I think, hey, could I put a mask in there? And oh, look, the code's pretty similar. I'm getting similar call stacks, but more efficient variants of it. So I'm finding VizTracer helps me be creative in understanding what's slow in my code and going faster as a consequence. Definitely want to go and try. Memory profiling is a journey that many people don't take, but of course with tools like Pandas taking lots of RAM, so 5x our regular RAM, it can be key to understand what's happening with our RAM usage behind the scenes, because that's pretty much non-obvious most of the time. You just don't think about it, you don't see it. Memory Profiler is analogous to Line Profiler. You can see in the bottom left corner, we get a line-by-line breakdown of memory usage on lines of our code. That works in the notebook and in modules as well. And I've written an extension tool, the IPython memory usage. That's the screenshot on the bottom right-hand. That only works in the notebook, and it tells you for every single notebook cell what's happening when you've run a single cell. You can see here we make a DF2, a new data frame from DF1 by multiplying it. It tells us we've used another 760 megabytes in a quarter of a second. Our total RAM usage is 1.5 gigabytes now, and whether there was a peak higher RAM usage during calculation, so whether background operations like a group by consumed a lot of RAM and then released it before we got to the end of the cell. That's great for diagnostics. What about compilation? So Numba is a wonderful just-in-time compiler. It works on our numeric Python code and our pure Python code. It doesn't really integrate around Pandas, but it can be used inside Pandas. And I've got a few slides on that. It specializes to your own CPU. You can pre-compile your code with ahead of time compilation. You could even compile to GPUs and run code in parallel on your own machine. One of the talks next week, High Performance Python with Numba, Dask, and Rapids by Gus, says that it will explain how all of this works in better detail. So you may want to go and check that one. Here are some examples. A Monte Carlo pi generator, so estimating the number of pi with a pure Python or a NumPy solution left and right. We've got the uncompiled versions at the top, and we've got the compiled versions at the bottom. You can see with the pure Python numeric code on the left-hand side, it takes 0.4 of a second to run. When compiled by putting the ngit decorator, and that's all you do, just one ngit decorator. You go from 400 milliseconds to 12 milliseconds, a 30 times speed up. And with the NumPy solution on the right, we take our NumPy code, 27 milliseconds, we compile it with ngit, we put the parallel equals true decorator option in there as well, so it runs across multiple cores, and we get 3 milliseconds, another huge speed up, another 10x speed up there. Super easy to use, and it works very robustly. So where are we with pandas? Oh, let me just take a quick sip. So where are we with pandas? You have to start thinking about pandas now as a platform, not just a tool. Other tools like scikit-learn and plotting libraries are building on top of it and using it as a base layer that we just expect to exist out there. This is kind of interesting because it means it's solidifying. It's becoming just a base layer of the foundations of the tool set that we use. It's got increasing integration of Numba. So you can't put Numba onto pandas functions, but inside pandas, you can use some Numba. I've got a couple of quick slides on that. Lots of things are quite painful still. Things like doing a group by apply is still hard and painful. You can make it fast, you can do some tricks, but it's really quite a lot of work. Some of the work being done there is to introduce the arrow data types from the Apache Arrow project. And one of the interesting things there is introducing a new string data type, which is much faster than the pure Python string data types. If you get stuck with slow string processing, there is now a new optional string D type in there that you could use. And parallelization is hard, and Dask could give us some nice options there. But there's a talk, Bodo, a new tool that I hadn't seen before. It's being demonstrated next week at the conference. That promises to give us MPI, so message passing interface, and Numba built-in support around Pandas, so an auto Pandas compiler and parallelizer. It looks like a commercial tool with a free usage. I know nothing beyond it. I've read some of their benchmarks. It looks really interesting. I think that talk is well worth attending. So just a quick example, if you take the rolling function, a numerically bound operation inside Numba on time windows, so rolling windows that move through time, traditionally, those operations have been really, really slow. Now we've got Numba support in there. If we just use the Python compilation engine, it could do some compilation. This is the old way of doing it. We might get a function running in 5 seconds. If we turn on Numba compilation and then get past the first just-in-time compilation step, we can get down to 0.1 seconds. So that's like a 50 times speed up. That's a huge improvement against, say, the Python alternative. That's a really nice improvement, well worth thinking about. You have to start looking in there. Not all of these Numba optimizations are advertised, and some are quite optional, but they're in the documentation. Dask is the final thing I want to talk about. We've got 6 talks coming up at the conference next week on this, so it's really becoming very popular. It's a rich library for wrapping up data frames and NumPy arrays and arbitrary Python functions. It's typically only known for Python data frames, but it does a whole bunch of different parallelization options that can run on a single machine or a large cluster of machines. And one of the talks will be given by April Rath, who's on this call. I had the pleasure of working with April's team earlier in the year, super bright team. They're going to have a really interesting story to tell. So I think you should attend that talk. It's great for scaling up your pandas data frames and your arbitrary Python calculations, and it's quite debuggable, and it's really mature now. You get things like this nice debuggable output, and you would definitely want to use it if you've got a larger than RAM problem in pandas. The way that I've used it successfully is that I've got data that I could barely fit into RAM or just doesn't fit into RAM, and I can split it up into smaller partitions with pandas and Dask, and then just run the same calculations over multiple partitions, and it just works. The results get glued together. I get a pandas data frame out the other side. It takes a little while. There is definitely a speed overhead, and that can take a bit of getting used to, but you get a really nice result out the other side. There are some alternate Dask pandas-like tools that are worth mentioning briefly. I really want to like them. I really, really want to like these other tools, but I'm always a little bit cautious with them. And one of the reasons I'm cautious is once you go off the beaten path and you use a less popular, newer alternative, you've got a new learning curve. And these tools fit themselves into parts of the ecosystem where Pandas scales badly. And that's brilliant. If you've got a Pandas scaling problem, then the likes of Vaex and Polars can scale you better. And that's excellent. But it also means you've got fewer users and a younger tool set. So possibly a less well-developed API or a less rich user base behind it. So these tools are definitely worth experimenting with. Vaex, great for medium data. It keeps your data on disk and then it pages in just enough into RAM to do your calculations. So it works just like Pandas, a very similar API, not the same, but very similar, pretty easy learning curve. And you can process data, particularly string data, super fast, much faster than you can in Pandas. So great if your data fits into a large RAM system or doesn't fit into RAM, then Vaex is a really good option. And Polars is a new in-memory Pandas-like system with a Pandas-like syntax. It's a less similar syntax, but it's still pretty similar, using the arrow data types only. So not using the NumPy data store that we're used to in Pandas, but using the arrow data types. So a different representation, a different way of storing that data, but a much cleaner, new, fresh API with a coherent design behind it, rather than the rather evolved API that we have in Pandas. So it's certainly interesting, but again, young. The author, Richie Vink, is giving a talk for us next week, and I'll be attending that, and I reckon you should as well, because hearing about a new clean design on a Pandas-like world is pretty compelling, but you'll still get fewer users in the younger system. So be cautious, but definitely experiment. So that first line there, reflect, debug, profile. I've been spending a lot more time thinking about my development process, my actual process, not finding the fastest tool, but how I use those tools. I found that reflecting on the tool that I'm using and trying to figure out, am I using it right? Am I doing the right problem? Am I solving the right problem? Can I debug it efficiently? Can I, get confused by a group by, so I can do a dir on a group by, because a group by is an object in Python. I can get in there and I realize there are groups. I can pull those groups out of a group by. I get data frames that I can call the aggregations on those data frames, and I can see how a group by and an aggregate is actually working. I can do it by hand myself. And that's really quite powerful. And then if I profile the process of Pandas processing my data with a tool like Vistrace and see that stack with everything falling out of it, I kind of understand the whole system from the bottom up. So I go slower, but I go faster overall, because I'm thinking more about the kind of the holistic approach to solving my problem and everything going on behind the scenes. So I think pulling apart the underlying tools with those profiling tools and then building up just a better mental model and understanding how you're producing your solutions is a more effective way to develop overall. So let's wrap up. On my blog's a bit out of date now, but all of my past open source talks are all listed on my blog. Please go and consume as many of those as you like. The slides and the videos are all there. I've got a newsletter which is very up to date that runs every 2 weeks. That's linked on my blog, and I'll put a link to that into the chat window. Every 2 weeks, I post about the topics that interest me as a senior data scientist, and that includes a lot of high performance stuff. So if you're interested in high performance stuff, you may want to look at that. I always ask at the end of my talks, now you'll see on the wall behind me a bunch of postcards on the wall. I've got them all around my office. These are from people sending me postcards saying, hey, Ian, you taught me something, have a postcard, I'm up a mountain. Brilliant. If I've taught you something and you'd like to send me a postcard at any point in the future, send me an email. I'll send you my address. I'd love to receive a postcard. So thank you very much for listening. We can open to Q&A now, and I can drink some more tea and soothe my poor throat. I'm curious in hearing about what blockers you have. Have you had success with tools like Vaex or Modin or Polars or Rapids for GPU acceleration? And what holds you up with tools like Pandas? Can we unblock any of that? All right, thank you very much for listening. So if you've got a question, you can do the hand up thing inside Zoom. You can post into the chat window, or you can just unmute yourself and say hello and ask your question, and that's totally cool as well. April, you got your hand up. Brilliant. That means I can have some tea. Go ahead.
So, your last question is where do we get stuck with Pandas? What are some of the challenging parts in terms of performance of Pandas? And I think the area that we continue to see people struggle with, where we see the biggest performance bottleneck, is around apply. So very interested, and I guess it's really apply, merge, and join are really the ones that I think are the killers in most cases, where we see a lot of time and effort being spent. Maybe we just start with apply. How do you recommend that people attack that problem? So they can see the applies are extremely slow. They're the biggest part once I've done profiling. What are some good approaches that people can use in terms of strategies for working through that and coming up with solutions?
So apply is fundamentally slow, so that's a problem, right? And I mean, this is something that we talked about during some of the training, different ways of approaching apply. And so one thing that I teach is if you've got an arbitrary apply function, well, there's different ways of breaking that down. One is to go down the route of using Numba to compile a function. Numba will compile a pure NumPy function, but it won't compile a Pandas function. So you can't use shift, for example, to shift the time series back by a day. But if you've got two NumPy arrays, you can offset your index by square bracket :1, and then you've got the same offset by 1 index into that array. So you can have your underlying NumPy arrays compiled by Numba and then passed as a function into a Pandas apply with the raw equals true flag. And then you get your Numba-backed compilation speed benefit, so a 10x speed benefit. And if you've got large arrays behind there and you turn on the parallel option, then hopefully you get a 10, 20, 30 times speed benefit coming out. So that's one thing we can do. If your calculations are really slow, So really, really slow. You've got a wide set of columns, and you're doing some Monte Carlo resampling and something like this, and it's doing just a big job. Then putting it into Dask and then in memory distributed data frame, and then running multi-core is one option. There is a big overhead there. You have to have a much slower function to take advantage of that. But if you've got a big data frame and it all fits in RAM, or you can spool it to disk, and then you can parallelize your computation with a Dask distributed apply across those distributed data frames, that definitely works, and I've done that with success. And the other angle is to step back and say, well, do I need to write an applied function? Can I decompose my function and vectorize the underlying operations? Because the vectorized operations are all very fast inside Pandas. And I've done a couple of benchmarks for my course looking at different ways of doing group by applied functions versus pre-calculating with vectorized operations some of those components, and then applying just a small applied function afterwards on those vectorized components. And you get a huge speed up if you can do that. Doesn't always fit. It can make the code more complicated. You have to think it through. It's not as easy and as nice as we might like. That Bodo.ai talk that I linked to, that promises to scale a bunch of this stuff up. I don't know if it works. I haven't tried it. I haven't seen it before, but the benchmarks on their site look very good. And it would be nice to see some more automatic parallelization and compilation inside Pandas. And I'm hoping that's what they've done. Does that mix with things that you've seen and used internally, April?
Yeah, definitely. I think, there's always that question. I think we always start with in some ways, we often start with is apply our only option? Is that our only way to think about it?
It's the easiest option, yeah.
It's the easiest. And I think, again, when you start with working with them, it's what you go to, right? You're just working in the Pandas API. It's what I got to do, and I've got to try it. I think more often than not, it is the source of most of the problems that we see from a performance perspective. And by having kind of a set of tools, a set of kind of things that people can work through in terms of strategies, it really helps us to consider alternatives even from the start.
And you mentioned join and something else, I think.
I said join and merge, because I think, again, the normal life cycles, right, are like my custom functions, and then I'm bringing data sets together. And those are often, I think, problematic.
Yeah, sure. And so join is a specialization of the merge function. Merge works on indices or regular columns, either or. And from my benchmarking, if you merge on, say, an index to a column or a column to an index, depending on whether you have repeated or non-repeated items and the size of the left and the right side of that merge, you can end up with a factor of 5 difference in your merge results time, even though you get the same result out the other side. And I wish I understood the rhyme and reason behind this, and I simply don't at the moment. There's clearly going to be some good engineering reasons why this works, but depending on the data set I put in and whether I have repeats and no repeats and missing items, then you can see some quite big 5x performance difference for the same operation. And my best advice is, hey, profile it and try the different variants. And it's kind of boring advice, because that's just the very manual schlep you have to work through. Sometimes it's worth it, sometimes it's not. Knowing that there is possibly an improvement to be had there is nice, rather than being blind to the possibility that there's just changing your index or not index options and combinations might give you an improvement. But that feels like something that should be faster. I've seen some benchmarks that suggest that tools like Vaex are better, arguably better, at doing joins on large data sets. So it might be that a mixed mode operation, do a bunch of your work in Pandas, write out in a Vaex compatible data form, because Vaex tends to like HDF5, and then do some of your expensive operations at the Vaex level, and then spit out something that you put back into Pandas like a Parquet file. It's a bit of a mess maybe, but that might give you actually a smoother workflow for some of these options. And Polars, I don't know where Polars wins or doesn't win, and I'm keen to find out some of that next week. It might be that for some of those options, writing out a Parquet file, so putting out the data in the same format that Polars wants and that NumPy is pretty familiar with, and then doing some of these operations in Polars and then going back into the Pandas ecosystem, that might be a good workflow. So I've got my eyes open to new possibilities for some of these talks next week. So in the chat, I've posted a couple of links, including the high performance Python cheat sheet from my course. So you're welcome to download that and take a look at it, and link to public talks. Well, I've also linked a different video. So I didn't say at the beginning, I'm talking about the viewpoint of a single data scientist or quants trying to crunch some numbers on a single machine, possibly a large machine, but a single machine. There's a talk by Matt Rocklin and Peter Wang talking around Dask's place in the wider corporate ecosystem. They talk about Python putting on a suit and becoming a bit more formal, and then working alongside Spark and the like, and so not being quite so much the happy hippie hacker, but the more corporate citizen. So it's an hour-long talk looking at the wider ecosystem. That's one that you might want to go and consume. So Patrick, you said, can I say a word on multiprocessing? Multiprocessing, I'd rather not. I can say another tool that I think is easier to use than multiprocessing. There's the multiprocessing library, concurrent.futures, etc. So I have a one solid chapter in my high performance Python book on multiprocessing, where I went too deep one Christmas trying to do things like use signaling to make a multiprocessing primality detector go faster via collaboration, and went way far too down looking at bytecode optimizations and the like, trying to make this thing work better. And then when I stepped out of that, I realized I'd never written any code that actually used any of these kind of techniques. I just went far too geeky in that chapter. That chapter exists so that no one else ever has to go and do that bit of work again. What I do find that I use out of multiprocessing, and most people use, is just multi-process, so multiple processes to spawn out some embarrassingly parallel work. So if I've got 50 pieces of work to do and I've got 4 cores, I can just spin up 4 cores running 4 jobs, consuming off some kind of queue. And JobLib is a brilliant tool for that. And I didn't include that. It's the one thing I nearly added an extra slide, but I didn't want to start overstuffing my slides. JobLib, J-O-B-L-I-B, is a brilliant tool for that. It wraps up multiprocessing. It makes it friendlier for notebooks with anonymous functions, which multiprocessing can't handle. And it works cross-platform very nicely. And it's got a slightly more efficient pickling library built into it, Cloud Pickle, and Loki for some concurrency manipulation. And it's basically, it wraps up a bunch of multiprocessing, and it makes your life easier with a one-line call to embarrassingly parallelize a piece of your code. So if you've got a function and you want to pass in some arguments, which could be a folder full of Parquet files that you want to process, or consume from SQL queries or whatever, it will all come in via JobLib, and you'll get a list of output arguments that you can then assemble into something. And the delayed nature of JobLib looks just like exactly like the delayed nature of Dask. So I teach JobLib as the entry point into Dask if you want to go into a bigger, stronger, more resilient, more scalable, but harder to learn framework on the Dask side. So JobLib is a super good one to go and have a look at. And then some nice words from Nadia. Thank you very much. Patrick, can I say a word on which one to use for embarrassingly parallel processing? Oh, well, I've answered that one already, JobLib. So JobLib is the, if you're on a single machine and you've got a function, which calls other functions, which will consume multiple inputs. It could be arguments that are passed in. It could be files on a disk. It could be spawning off multiple SQL queries, whatever. If it's running on one machine, JobLib is the simple answer there. And with JobLib, you can tell it how many jobs to run in parallel. If you say n jobs equals 1, it turns off all the multiprocessing stuff so that you only have a single for loop processing the arguments that you're passing in. And that means you can put a breakpoint in there. And JobLib comes in a single module. Everything's in a single module in one class. So you put a breakpoint in there and you can step through it in PyCharm and debug the whole thing. And then when you know that it's working on your small subset case, you can do n jobs equals 128 because you've got a huge many-core machine, and then kick it off and it will run in parallel. A bit harder to debug, but at that point it's running and you're happy. If you've got a multi-core problem, multi-core, multi-machine problem, then Dask delayed, I would suggest, is the way to go. How does Dask compare to Spark? I say that Dask is Spark's younger brother, and it never aspires to become the older brother. Spark covers the huge, wide ecosystem of the corporate landscape and wires in many components and many technologies. Dask doesn't try to compete with all of that. It competes with a small subset of that. What Dask gives you if you're operating mainly in the Python world, is the Python language to debug rather than Python and Scala and maybe some Java. So you keep yourself in one environment. And if you've got a Dask local cluster on your own machine, you don't have to hire another engineer to run your Spark cluster in the background. So your operating costs and your complexity come down. If you've got a huge data set and you benefit from using the wider, richer Spark ecosystem, and those things don't exist in the Dask world, you're not going to get them, at least not in a hurry. Maybe you do need that wider Spark ecosystem. But if you're dealing with data that fits on one machine, possibly a large centralized machine, or a cluster built around that, and you can live inside the pure Python world, then Dask gives you all of that. And it's really quite mature for that use case now. Right. Amrit, the main blocker I have with Dask is in scaling it up to multiple nodes. Do I have any good resources for deploying it in production? No, I don't. I use Dask on a single machine basis when I'm working on it. So I haven't tried scaling it up to multiple machines, but I suggest that we've got 6 Dask talks coming up, including April's, and it sounds like some of these topics will be covered there. So hopefully scaling will be touched by April and others over next week's talk set. And Jin Taktan, what is your view on Cython? Is it still a relevant library? Oh, good question. So I didn't touch on Cython. So Cython is the older compilation technology. The first edition of the book had a much bigger section on Cython. I reduced it for the second edition because Numba has grown up and I think is more useful in the quant and data science crowd now. Cython lets you write in a Python C meta language. So it's Python, but with C declarations around it. That code gets read and translated into C code, which then gets pushed through a C compiler like GCT, and you get a static library out the other side. And so you get the benefits of compilation. If you don't provide the C type declarations for your integers and floats, then you get a Python object. So you compile a bit of Python, but it doesn't go any faster because it's still a high-level Python object with all of its generality. If you say, oh, this particular thing is an integer and this particular thing is a float, then Cython can say, oh, right, make that an int 64 and that a float 32, and then it will run at C-level machine code speeds rather than the interpreted Python speeds. And so you can write that Monte Carlo Pi generator code that I showed with a few extra lines of Cython declarations, and you'll get the same speed up out the other side. Cython is very mature, so I can parallelize my code. I actually have richer control over OpenMP parallelization. I can choose different schedulers, which I can't do if I'm using Numba. So you do have richer and deeper control if you use Cython over your Numba code, but you have to write more code. And debugging it is quite difficult because then you've got C to deal with, and profiling it becomes really difficult. Actually, you can't profile Numba code. You get no profiling output, so you simply can't do that. You can profile your Cython output, but it's quite involved. I used to write Cython code, particularly for making physics code faster. And then when I found Numba, and Numba used to, like 8 years ago, it used to crash a lot. It used to crash on very small functions. So it got a couple of pages in my book. Now it gets a section in my book and another section in a different chapter by one of the core developers, because it doesn't crash and it just makes your code fast. So you can easily put ngit around your function and ngit around any functions that are called inside it, and you get a 10x or a 50x speed up. And if you've got multi-core and you've got a for loop that's doing, I don't know, 1,000 iterations, and it can spin each of those iterations in an embarrassingly parallel fashion across those different cores, you'll get your 100x speed up on your 100 cores. And you get it by just putting an ngit decorator around your code. It's brilliant. Does Cython have a place? Cython's one other string to the instrument is that you can call out to external C and Fortran libraries via Cython. So you can include them just like you include a C header. And that's pretty interesting. If you've got existing C Fortran code, Numba will not let you link out to an existing C or Fortran function. So if you've got code that someone has written and you know, it's nice, fast math routines perhaps, and you want to use those, Cython is the way to go. But for everything else, I think Numba is a really good, sensible choice. I
Yes,
see. Oh, please, yes, go ahead, ask the question.
Thank you. I deal with big data sets quite a lot, and interestingly enough, I like doing things in the Python ecosystem if I can. And so I work for a bank, and we have these absolutely incredibly massive data frames that we get from the warehouse, right? And now, we want to do our machine learning stuff on it. And the thing is, I'm basically the only one who really knows like things like parallel libraries like Dask and all these other things, Modin. Everyone else just knows Pandas. Now I said, okay, now we need to write functions that can parallelize these things. And at first I was like, well, how can I make them write Pandas, but it still scales on this multi-core massive server? And the first thing that if you Google, you get Modin. And funnily enough, I just found Modin to, I don't like. Modin just struggles. I don't know, for some reason it just doesn't speed it up. I can't tell you what's wrong with it. Aside from resort, and then other things I found to work quite well then was things like DuckDB, which allows you to write this in memory OLAP database, right? And then you realize, well, if the only thing that scales this massive data set that I have to work with is SQL anyway, you might as well stick to the warehouse that your company gives you. So where do you draw the line between this? It's just too much data. Going and taking Pandas ecosystem stuff is kind of working backwards. This where you join these massive tables, just do it in the warehouse or the SQL server, whatever you have. You kind of bringing tool sets where it doesn't belong. Where do you draw that line? Thanks.
Thank you for that. You've got some good observations there, and thanks for sharing about Modin. I do wish that Modin would just be a great solution, because you just from modin.pandas import pandas, and you get a wrapper around pandas from the Modin side, which promises column-based parallelization, and it should just work. But in my testing, some of it works, some of it doesn't. Sometimes it crashes, and when I've asked around with colleagues, that's the general answer I've got back from other people, and it's really frustrating because I want it to just work. Unfortunate that you've had a similar experience, but good to hear. So where does one draw the line? You're the second person in a week to say that DuckDB has solved some of these scaling problems, which is kind of interesting. Keeping the data on disk and running this Python-friendly OLAP query system there. It's definitely, so it's not on my radar, but it's becoming on my radar as it's being mentioned by others. I mean, why do we pull things out of SQL into Python if everything we need to do can be done on the SQL side? Leave it in the SQL side. It's probably the right place to leave it. And if you can just do your queries and your manipulations there, and then get the data that you need out for, say, a machine learning system, that's brilliant. That's fine. It solves the problem. I try to be very pragmatic in this kind of thing. I'm not a zealot about the use of Python for everything. Also, my brain is small and there's only so much I can fit into it. And if I can get stuff out of a system and then put a snapshot into Python and work on that snapshot, hey, it turns out my mental model is simplified and I can do things there, which can work in a research context brilliantly. So I think there's always there's a tension between research and engineering. If I want to play with an idea and I can get a subset of my data, play with it in Python pandas. And then when I've figured out what it is, the problem that I'm solving, then I want to implement the more engineered system that scales. Maybe, depending on the data set size, maybe a Python solution isn't the right solution anymore, and pushing out to another tool is the right solution. Pandas gives us great and very flexible time series manipulation, and not all SQL systems give us that flexibility, or they make it painful. And so scaling it is doable, but it's not a creative research endeavor at that point. You have to go and engineer some proper code to do it. And so that can break the research workflow. So doing it in Pandas and doing it with Dask, and it might be a clunky step up for the scaling, but once you've got Dask working, because there is definitely a step up in there, that scaling headache, and you try to use all of your Pandas functions in Dask and not all of them work, and then it breaks and you get weird things happening and you have to go and figure it out. Once you've figured it out and you've scaled up to the next level, it's brilliant. But then I want to productionize it, and maybe SQL is used by the organization. So again there, maybe engineering it back into SQL is the right solution. So I don't know what the right answer is, but I wouldn't be afraid just to go back to a boring technology that works if I've got a simple problem, one that I understand, that can be expressed in that boring technology, because boring technologies just work every day. And if you keep the data in one place and you've got a big team that could support it, brilliant. It's not my support problem anymore. And that's excellent as far as I'm concerned. I'm not a fan of researchers writing code, chucking it over the wall and making it somebody else's problem. But sometimes from a scaling perspective, that's not a silly position to take. Does that help? All right.
That's perfect.
Cool. Rashid.
Yeah. Hi, man. How are you?
I'm very good. Thank you. How are you?
Yeah, I'm doing great, man. Actually, I have one doubt. I mean, with this advancement of distributed systems like blockchain, there seems to be, one more layer needs to be added on this as a data layer, okay, on this data analysis process. So my question is actually how we can, how we can implement the scalability, because this, this Web3 world is slowly, it's developing, and it's adding another data layer to the existing system, and we are we are dealing with these large data sets, and how we can integrate those things, because when I researched for many, but I couldn't find a community or a research paper, anything related to this. How we can,
when you say what kind of scaling you're talking about? You mentioned blockchain somewhere in there, and you mentioned scaling, and I'm not sure
absolutely, because means actually in the distributed system, actually there is one more layer, it is adding, because it's security layer, one more, this blockchain, if you are integrated with the system, then there comes a point in which it adds another layer to the system. Okay, so it is making a much complex. So what I'm saying is, when we are dealing with the distributed system to access data and with this complexity, how we can make this entire analysis scientific computing process in this ecosystem like blockchain. I mean, how we can bring those things in like blockchain. That's it. Simple as that.
Well, all right. And I apologize. Yeah. I don't have an answer for that. I know nothing about integrating into
because I no worries, man. Sorry for the interruption. Because I see that but because blockchain, it is changing the entire way we look at the things. Okay, so we need to be focused on that. That's why unlike in any other development, this is taking place and the entire system is changing. So I'm really curious to know how they are bringing to the scalability and those things to the distributed system like blockchain ecosystem. So I googled it, I researched a lot about it, but I'm not finding a way or community yet so that I can just start actually, because there is nothing is there. Yeah.
So I don't know of anything, and none of my client conversations have led me down that avenue, but it doesn't mean that others aren't talking about it, of course. If you want, in the chat window, stick in your contact details, and maybe somebody else on the call would.
Sure.
You're welcome to do that, but I have no opinion on that, I'm afraid.
No worries, man, because I always ask this question to conferences and everywhere, so that I can get an answer and I can start with, because just now it is just starting, but I'm really curious to know, because everything we look at the things, web is changing to another level, also the systems and everything are changing to another level, and I need to know, how we can focus and from where we can start, all those things.
Yeah, no, I think put your contact details in, and maybe someone else has gone down that avenue.
Sure, man. Let me. Oh, okay. Here goes.
Sure.
My email ID. Yeah, man.
Okay.
Thank you. It was a nice session anyway. I'm glad to meet you.
Thank you very much. I'm glad it was helpful. Good. Cheers. And there was a question in there. Any recent updates? I put in the third version of the book. So Viz Tracer that I mentioned during the talk, that's not in the book. And it was kind of on my radar. It was another profiling tool. I didn't really mess around with it. Having started to use it, I mentioned I used the word creative when I touched on it earlier. I found that if I say I've got a group by in a function and it does something, and then I visualize it with Viz Tracer, and you see this stack. Let me just share my screen again. I'm going to go off slightly on a tangent for you, but possibly it will inspire you to go and try it, the tool, because I think that is kind of interesting. So, right. So if I go back, that's VisTracer. So at the top there, I've got getMean for indicator variant 1. So a function that does something that's, I think there's a group by behind. Is there a group by on that one? There's no group by. No, that may have been my query. That may have been my query variant. And so I was trying to solve a silly problem, showing how pandas can be quite expensive to use in one of the exercises in my course. And I ended up playing with a couple of different solutions and visualizing them in VisTracer. And I got a bunch of these plots, and they're side by side. So you get kind of this flame graph falling down the screen for indicator variant 1, indicator variant 2, group by variant, blah, blah, blah. And then as you run your mouse up and down these variants, if you've got the same sequence of functions in the flame graph, they get highlighted across all of these different parts of the call sequence. So time goes left to right, so you get a bunch of these things falling down the screen left to right. And then as you move your mouse over one bit, other bits get highlighted. And I looked at that and thought, oh, right, look, I've got my my query process over here, felt like the fast one. And then I tried a mask generation process, and oh, look, well, that masking code is actually hidden behind the query code, and the query code does a bit more. So my query code is a superset of the mask code, and the mask code runs faster, but I can see it's doing exactly the same job behind the scenes. And I kind of knew that because I've read the source code before, but I didn't really know that was the case. And I could see it presented on screen. And alongside it, I've got my group by variants and some other variants. And I can see little bits of that code stack also being highlighted when I'm rolling my mouse around, thinking, oh, it's kind of weird. So bits of what's happening in the group by are actually happening in this query as well. And it caused me, just thinking in this visual way, to start creatively thinking about other solutions to this problem, which I might go and try in a way that I've never really had when I've been using line profiler. So line profile is brilliant to highlight what is slow. So if I've got 50 lines in my function, I think line 10 is slow, and it turns out line 20 is slow. I want to work on line 20, not line 10, or I'm working on the wrong thing. So line profiler tells me the problem, but it never caused me to like spark off new thoughts. Whereas this VisTracer in this more visual way, opening up what's happening behind pandas, that made me think in a more creative way. So that's not in the book. That will definitely be in the next edition of the book. The book doesn't have any of the pandas competitors, so Vaex, Polars, and Modin. I don't know which one would be included. I mean, the first version of the book didn't have pandas because pandas wasn't mature at the time that we wrote the first edition. These tools are becoming mature now, so hopefully they'd be in the third edition. I certainly think Vaex and Polars are worth an explore. There's a bunch of previous Vaex talks at PyData conferences that are worth catching up on, and there's the Polars one next week. So I don't know, but I would imagine they would both feature in the next version of the book. Rapids as another pandas-like system, which works on a GPU, that will probably feature to some degree. The first edition of the book said, don't use GPUs. They're really, really hard to program, and there's no general frameworks for it, and it's really hard to fit it all in your head. I used to write CUDA code by hand. And then it turns out along the way, TensorFlow turned up, and all the related libraries, and of course, GPUs became super popular, and the book looked a little bit dated there. So the second edition of the book says, hey, use some of these libraries and write general code in a library that will compile the GPUs for you. That's very sensible. But it doesn't touch on things like Rapids for GPU-based pandas-like acceleration, which is a pretty niche use case. You're really good for the same kind of financial time series data, perhaps, but not for your general pandas manipulations. But as our ecosystem widens, we'll find more and more niches that need these specialized tools. So I imagine Rapids will add in there. Can I think of anything else? Off the top of my head, I can't think of anything else that I'd put in. Something I added to the second edition was a reflection on what I think it means to be higher performance, or to be in a higher performance mindset. So writing unit tests, reviewing my code, thinking about whether I'm solving the right problem. Whereas earlier in my career, I've happily made things 100 times faster and then discovered that I get a different result. So I've made something fast, but wrong. And of course, that's no good. So, am I solving the right problem? Am I solving the right problem sensibly? I suspect I would seek input from more people to expand that for a third version of the book. Because I think a lot of people inefficiently solve problems. So getting a team to run a retrospective on itself to not ask, are we engineering our solution correctly, but Are we even working on the right problem? Are we using the right wider tool sets, given what we've learned about the problem so far? So that kind of higher level meta thinking about the process of our craft. I think I'll add more of that into the book, because I think that kind of introspection's kind of powerful as well. If we've got no more questions, then Comrade, I think we might want to draw this to a close. Thank you very much, everyone, for attending. Thank you for the questions, very good and interesting questions. I'm happy to catch up with you, hopefully, via the various social options that we have for the conference. Thank you very much.